So an exponential equation would be something like 3 to the x equals 5 because it has an expression in it that has a variable in the exponent. Another example might be something like the natural log, oh, that's a 2. The natural log of 6 equals 3 minus x. Actually, let's do this. The natural log of x equals 6 minus 2x. That would be an exponential equation. Right? On the right, we've got the steps for solving exponential equations. So these are the steps that we usually follow. Okay, 90% of the time. Okay, the first thing we need to do is isolate the logarithm or exponential if we can. If we can get the logarithm or the exponential by itself, then we're in good shape. Then we're going to eliminate the logarithm or exponential. We're going to try and eliminate the exponentials and logarithms because they're a little bit easier to solve, usually without them. And then we're going to solve for whatever the variable is. So quite often we end up with a problem that is simplified down to like an Algebra 1 problem. Okay, so that's what our goal is for most of these, is to get it down to something simple that we've seen before. Yeah, right. First example, 4 to the x minus 1 equals 10. All right, well, so the first thing I got to do in my steps was to get the exponential by itself. So what do I have to do first? Add 1, right? So when I add 1 to both sides, I get 11 equals 4 to the x. All right. So now, how do I get that x out of the exponent? What if I took the log base 4 of both sides? All right, then the bases and the logarithms cancel out on the left, and I get x equals the log base 4 of 11. Problem out, we would just then simplify this to x equals the log of 11 divided by the log of 4. And you can punch that into your calculator, and what do you get when you put that in your calculator? 1.73. This is method 2. You might write that next to it if you're going to take notes on it. Method 2. And there are cases when this is going to be a little bit easier method to use. The first step is still the same. Get the exponential by itself. So I get 4 to the x equals 11. And then instead of taking the log base 4 of both sides, I'm going to take the common log of both sides. An okay algebraic move because I'm doing the same thing to the left as I'm doing to the right. So I end up with the common log of 4 to the x equals the log of 11. And then what can I do with that x then? Now I can take this x and put it out in front, right? So this is x, actually be x times the log of 4 equals the log of 11. Well, the log of 4 is just a number. It's something I put in my calculator, so I'm going to divide both sides by the log of 4. And I get x equals the log of 11 divided by the log of 4, which is hopefully what we had before, which is what, 1.73. So since they're both log base 5 on each side of the equation, I can take it's called exponentiating. I can exponentiate both sides with a base of 5. So I take 5 and raise and put log base 5 4x minus 7 in the exponent, and then base 5 and exponentiate the right-hand side. And so I end up with this 5 log 5 canceling on the left and canceling on the right, and I end up with just 4x minus 7 equals x plus 5.
Can you do that again?
Let's finish solving this thing. I'm going to add 7 to both sides. And I get x equals 4x minus 7. That's not what I get. 4x equals x plus 12. And then subtract x's, so I get 3x equals 12, and then I get x equals 4. Like I said, we should check our answers. This is in fact a solution. X equals 4 is a solution. So it checks out okay. So I have log base 5 of 5x minus 1 on the left equals 3. I've already got the logarithm by itself. I don't have to... Yeah, so now we're just going to exponentiate, right? Both sides with a base of 5, so I end up with 5 cubed, that's gone, equals 5x minus 1. So I get 125 equals 5x minus 1. If I add 1 to both sides, I get 5x equals 126. And a little mental math here tells me that x then will equal 25.2. I've got 2 logarithms on the left-hand side. I've got none on the right. I can't really get either one of these logarithms by themselves, but I can take 2 logarithms and compress them together into 1 logarithm. That's what we just worked on. So how do I take 2 logarithms that are added and compress them to 1 logarithm? Yeah, so I'm going to take the log, this is the common log, which is base 10 since we didn't write a base, of 2x, we'll put some braces around it here, 2x times x minus 5 equals 2. Got to get rid of that logarithm. We know that if I don't write a base, it's log base 10, or we assume it's base 10, so I will exponentiate both sides with a base 10, and that gives me 10 to the 2 power, I think is 100, and then I get just 2x times x minus 5 on the left. Now, I want to get rid of that 2. I don't have to. I could distribute right now, but it's going to be a little bit easier if I get rid of the 2 right now. So this will simplify to 50 equal to x times x minus 5, and then we'll deal with that in a second. Okay, so now I've got to distribute the x, and I get x squared minus 5x, minus 5x equals 50. And then this is a quadratic, right? And to solve quadratics, we need to get them set equal to 0. So I'm going to subtract 50 from both sides, and I get x squared minus 5x minus 50 equals 0. Okay. This is going to factor into, x, and then numbers that multiply together to give me 50, but combine to give me negative 5. Yeah, x minus 10 and x plus 5. Once I've done that, my 2 solutions are x equals negative 5 and x equals 10, right? If I plug in 10, I get 0. 10 minus 10 is 0. And if I plug in negative 5, I get 0 also. Here, let's check x equals negative 5 first. So check x equals negative 5. All right, here we go. Log of, that's going to be negative 10, plus log of, I think that's negative 10 also, right, equals 2. Someone click away on your calculator. Tell me if that's true.
Negative 5?
Negative 5 is not a solution, right? X equals negative 5 is not a solution. We can check 10. I'll give you a hint. It is a solution. Very quickly, log of 20 plus log of 5 equals 2. I promise you. I don't want you to make this any harder than it is. It's things like if I had 5 raised to the I'm sorry. Okay, don't worry, it's back. If I had something like 5 raised to the x minus 1 equal to 5 raised to the 2x. Right? All this is saying that is if the bases are the same, this can be simplified to x minus 1 equals 2x, and that's something that we could solve for x, right? If I had the same equation, 5 to the x minus 1 equals 5 to the 2x, and I took the log base 5 of both sides, notice what would happen. The 5s are gone, the 5s and the logs are gone, so I end up with x minus 1 equals 2x that way too. So you can either memorize the property or algebraically it'll fall out the same way. How do I make 9 and 27 have the same base? What base should I use? How about 3? So let's make 9, instead of being 9, let's make it 3 squared. Alright, so I'm just substituting in place of 9, I'm putting 3 squared. And then don't forget, we're multiplying by 2x. 27 is what with a base 3? 3 raised to the third power, right? 3, but don't forget, I've got this x minus 1 up here. Okay? So I've changed both bases so that they have the same base. I just have to be really careful with the exponents.
Yeah, why is the exponent 3?
Simplify this. Let's simplify this to 2 times 2x equals 3 times x minus 1. Quickly here. This is going to be 4x equals 3x minus 3. And so x equals negative 3. And you can check that answer if you'd like. I think you figure out that it checks out. Okay, so it's going to be a base 2. Take a second, try it, and then we'll go through it.